Hello, my dear GATE aspirants. I am Madhishekar, faculty at AS Online and AS Engineering Academy. I am here going to discuss about GATE 2026 Score Booster Series. In this YouTube session, I am going to discuss about NAT and MSQ questions. Okay, na? See, here I am going to deal with the material science. For GATE exam point of view, especially for mechanical, from the material science, two questions they will ask you. One question is definitely from the iron cementite phase diagram, numerical based question, and another question, there may be a theory type question they will ask you. So I will discuss some of the important questions along with this procedures concepts. Okay, now, right. Now let us consider the material science questions. First question you can take here. The question here, figure shows an X-ray diffraction pattern for lead taken using a diffractometer and monochromatic X radiation having a wavelength of 0.1542 nanometer. Each diffraction peak on the pattern has been indexed. Assume order of diffraction is 1. Find interplanar spacing in nanometer for each set of planes indexed. See here, this question is related to Bragg's law. Okay, this question is related to Bragg's law. So what is the basic formula of Bragg's law? What is the basic formula of Bragg's law? N lambda is equal to 2d sine theta. N lambda equal to 2d sine theta. See, from this question, the given data here, if we take X radiation having a wavelength of 0.1542 nanometer. So the wavelength is given, lambda is equal to 0.1542 nanometer. Okay, na? And order of diffraction is given 1. Order of diffraction is nothing but n. N is order of diffraction, that is equal to 1. Okay, now, and diffraction angle, okay, diffraction angle directly not given, but from the graph it is given. See, how to choose this diffraction angle, that is very important. If you see this wave formation, in this wave formation, there is a peak wave, you can take maximum peak wave, you can take this one, we should consider as a diffraction angle. So here I will consider the diffraction angle is 70 degrees. Okay, na? The diffraction angle is 70 degrees. So here diffraction angle 2 theta, that is nothing but 70 degrees. Then if 2 theta is 70 degrees, then theta is 35 degrees, right? Theta is 35 degrees. Bragg's angle represent theta and diffraction angle represent 2 theta, so don't confuse. Now here I am going to substitute in this equation. I want interplanar spacing in terms of nanometer. So here d is equal to n lambda by 2 sine theta. Okay, d is equal to n lambda by 2 sine theta. So from this, n equal to 1, wavelength is 0.1542 nanometer by 2 into sine 35 degrees. Sine 35 degrees. Now see here, I am using GATE calculator to solve this one. I am using GATE calculator to solve this one. See, in the numerator 0.1542 divided by, okay, na, 2 into sine 35 degrees. Okay, so here you will get 0.1344 nanometer. Because this numerator lambda is in nanometer, so that interplanar spacing D is also you will get in the nanometer. So they are asking interplanar spacing in nanometer. So this question we are solving by using this concept of Bragg's law. Okay, na? I hope you understood this question. Everyone got the same answer? Am I right? Right. Yes. Okay. Now, let us consider the second question. See, the lattice parameter for BCC iron. The lattice parameter for BCC iron is 0.2866 nanometer. Okay. And assume that monochromatic radiation having a wavelength of 0.1790 nanometer is used. The order of reflection is 1 interplanar spacing for the set of 2 to 0 planes. See, here in this question, the data is given like related to the Bragg's law, like order of diffraction is given, wavelength is given. So most of you people will try to calculate, okay, by using the Bragg's law equation, but in this case they are not given the diffraction angle. Then how to solve the interplanar spacing? See, interplanar spacing for a cubic, remember general interplanar spacing, formula, if I consider generalized formula, if I take D is equal to 1 by under root H by A whole square plus K by B whole square plus L by C whole square. This is the formula actually. But this is the generalized formula applicable for all types of lattice systems. But here for us it is given BCC structure. BCC structure is having a cubic type unit cell. Okay, BCC structure is having a cubic type unit cell. So for a cubic system, we are familiar that A is equal to B is equal to C. Now if I substitute in this equation, interplanar spacing D is equal to A by under root H square plus K square plus L square, right? Now we should use this equation. Now here in the question, lattice parameter, that is nothing but a lattice constant, is given 0.2866. Lattice parameter, that is nothing but a lattice constant, is given 0.2866 divided by Miller indices of a plane. See, remember they are given set of planes of 2 to 0. HKL is given 2 to 0. So here H is 2, so 2 square plus 2 square plus 0 square. I am using here calculator. Now let us consider under root 4 plus 4 8 under root 8. Now here from this 0.2866 divided by this answer, you will get 0.1013, okay na, nanometer, because this is in nanometer. So that interplanar spacing for this plane 2 to 0 is 0.1013 nanometer. So this is another way of asking question. I hope you guys getting this answer, right? I'll see here. Is there any comment? Please let me know if you have any doubt in this. I hope everyone got this concept, right? I'm going to start another question. Okay, everyone? Right. Now, let us consider the second one. See, another question. The crystal structure of gold is FCC. Okay, very good. The planar density on a 100 crystallographic plane is X. Okay, and planar density on 110 crystallographic plane is Y. Then which of the given below is correct? Then which of the given below is correct? Let us consider. I'll take 2 new slides here so that I'll get easily. Listen carefully. So they are asking planar density or linear density. Tell me, planar density of two planes. One is 100. Remember, one is 100 and the second one is 110 of FCC structure. So gold is an FCC structure. Let us consider, okay, planar density in 100. I'll see first. Planar density in 100 is X. So let us consider first of all a face-centered cubic structure. A face-centered cubic structure I'll consider here. Okay. The face-centered cubic structure, if I consider here, at every corner there is one atom. At every corner there is one atom like this. Like this. And at every face center there is one atom. Center of each face one atom. Like this. Okay. This is an FCC structure. Okay now. Now let us consider, this is origin I'll take. This is x-axis and this is y-axis and this is z-axis, right. Now Miller indices 100, if I consider the plane fractions of this Miller indices, I'll get by doing reciprocals 1, infinite, infinite, because 1 by 1, 1 by 0, 1 by 0, I'll get infinite, infinite. So what do you mean by this infinite, infinite means? The given plane is parallel to y-axis and z-axis and x equal to 1. So from the origin, locate x equal to 1, a point A. From this point A, it is parallel to the y-axis. Again, it is parallel to the z-axis. So parallel to the y-axis and parallel to the z-axis. So I'll get the plane like this. We can see it's a side of a, suppose if I take a cube, one side of a cube will give you, one face of a cube will give you 1, 0, 0. So let us consider this is the plane like this. It is the plane like this. Now how the atoms are arranged? At each face center there is one atom. So at the center of this face center one atom and at every corner one atom like this. Like this. Okay, now I hope you understood. Right. Now listen carefully. Here the area, if I take this area is, this is A, this side length is A and this side length is A. Right. So planar density and number of atoms, how many are there? Here it is one atom, here it is 1 by 4, here it is 1 by 4, here it is 1 by 4, here it is 1 by 4. So planar density that I am representing with x value, x is equal to, number of atoms in the plane is 2, 1 into 1 plus 1 by 4 into 4, 2 by a square. Okay, na? Planar density in 100 plane is 2 by a square. Right. Second, they are asking 110. Same FCC structure I will consider. So planar density in 110 I will consider. So same FCC structure I will consider here also. FCC structure I will consider here also. right? Now here, listen carefully. At every face corner, one atom. So 8 atoms are located at 8 corners. 8 atoms are located at 8 corners, and one atom is located at the face center. At every face center, one atom, like this, right? Now let us consider, okay, this is origin, this is x, and this is y, and this is z, right? Now if I consider this plane, the plane fractions of the given Miller indices, plane fractions are nothing but reciprocals of Miller indices. So plane fractions are nothing but 1, 1 and infinite. Okay. Okay, by doing reciprocals of 1 by 0, like 1 is 1 by 1, 1 by 1, 1 by 0, so that I will get 1, 1 and infinite I will get here, right. So from this, see here, from the origin x equal to 1, a point A, from the origin y equal to 1, a point B. So first draw a line of AB, one face diagonal. Okay, the given plane is parallel to z-axis, so that you can write from point A, draw a line parallel to z-axis, and from point B, draw a line parallel to z-axis. So this is the plane you will get. This is the plane. Now if you observe carefully, this is a plane of rectangle actually. So rectangle is like this. Okay, it is like this. Rectangle is like this. Now here how the atoms are arranged, you know, how the arrangement of atoms are there. This is one face diagonal, so there is one face center atom. This is one face diagonal, there is one face center atom. So the face center atoms are present like this, and at every corner atoms present like this, like this. Okay. Now from this, listen carefully. Here it is off, here it is off, here it is 1 by 4, here it is 1 by 4, here it is 1 by 4, here it is 1 by 4. And area wise, if I take, this is side length A, this is root 2A, it is a face diagonal, so that it is root 2A. So planar density, okay, planar density is equal to, okay, number of atoms in the plane is same, 2 atoms only, number of atoms in the plane is 2 only, but area is root 2 A square. So this is y. Remember, in the question, planar density for 1, 0, 0 is x, planar density for 1, 1, 0 is y. So x we got the value a by, sorry, 1 by, sorry, x we got the value, I will consider, see here, x we got the value 2 by a square, 2 by a square, y we got the value 2 by root 2 a square. Now tell me what is the correct answer for the given options. X is greater than y, x is less than y, x equal to y, and insufficient data. Guess the answer. Tell me, my dear aspirants, my dear guest aspirants, tell me the answer. What is the answer? Tell me. Yes, right. The answer for this question is A, because x is greater than y. X is greater than y, right? X is greater than y. Now, next question, you can take next question. See, the crystal structure of iron is BCC. Find the number of atoms per unit crystallographic direction. Remember, in this case, direction they are asking. Number of atoms per unit crystallographic direction in 110 length. Assume radius of the atom is r. Now, listen, in this case, iron is BCC. This data is given. So, the crystal structure of iron is BCC. So, let us consider BCC structure. Let us consider BCC structure. Now in BCC structure, listen carefully, there is one atom at the body center and at every corner one atom is there like this. So 8 atoms are located at 8 corners. 8 atoms are located at 8 corners. One atom is located at the body center. Right. Now my question is, linear density they are asking in 110 direction. Now I will locate the origin x, y, z axis. Suppose this is origin, this is x, this is y and this is z. Origin x, y, z. Now listen carefully here. Listen carefully here. X equal to 1. In the question it is given x equal to 1, y equal to 1, z equal to 0. So from the origin, locate x equal to 1, a point A. Then from point A, locate y equal to 1, another point B. Right, and z equal to 0. So draw a line from origin to the end point. From origin to the end point. Like this. They are asking 110. So what this 110 represent, it is a phase diagonal, XY phase diagonal. So in case of XY phase diagonal, otherwise you can take 101, same answer you will get na. So 101 if I take, this is the direction. What is the length of this direction, its side length is A. If I take this phase diagonal length is root 2A. Number of atoms, how many are there? Number of atoms, tell me. Here it is off, here it is off. Only one atom is there. One atom is there. Okay. So, linear density is equal to number of atoms 1 by root 2A. But in the question, A is not given, R is given, radius of the atom is given. So tell me, for BCC structure, remember, for BCC structure, what is the relationship between R and A? 4R equal to root 3A. So A is equal to 4R by root 3. So I am substituting in this equation, that is 1 by root 2 into A is equal to 4R by root 3. From that I will get root 3 by 4 root 2 R. Root 3 by 4 root 2 R. So out of these 4 options, tell me the correct answer for this question is C. Correct answer for this question is C. So one question we discussed regarding planar density, one question we discussed regarding linear density, and one question we discussed regarding Bragg's law also, right? Right. Now this is another question, it is related to theoretical density. So for GATE exam point of view, they will also ask you theoretical density questions. Am I right? Anyone knows the formula related to theoretical density? Suppose the density of iron, density of aluminum, how will you calculate? Guess? Anyone knows? Let me know. Will you calculate? Will you find the theoretical density? How will you find? Guess it. Now, see here, I will tell you theoretical density, how to find. What is the formula I will give you? See, remember, theoretical density of a metal is measured by considering the smallest block of the material. Smallest block is what? Unit cell. Okay? Smallest block is what? Unit cell. So, by using a unit cell, mass, that is weight of the unit cell, and volume of the unit cell, I will get the theoretical density of material. So, remember, theoretical density, that is rho, is equal to, okay, number of atoms into atomic weight by Avogadro's number into volume of unit cell. This is the formula. Okay. Effective number of atoms in the unit cell. AW means atomic weight. AN means Avogadro's number. VUC means volume of unit cell. Volume of unit cell. Right. Now, we'll read the questions here. Copper. Tell me, what is the crystal structure of copper? Anyone knows? The crystal structure of copper, anyone knows? It is given in the question itself. Okay. It is FCC structure. Copper is FCC structure. Has an atomic radius of, so remember, FCC structure is given. So you will get to know some information regarding FCC structure. Then only you can solve this question, otherwise you can't. What information you know? The number of atoms, the effective number of atoms in the FCC structure is 4. And the relationship between R and A is 4R equal to root 2A. 4R equal to root 2A. From that, A is equal to 2 root 2R. Okay, na? A is equal to 2 root 2R. This information, if you don't know, you can't solve this question. Okay. Now, see, atomic radius is given in the question. Radius of the atom is given 0.128 nanometer. Okay. FCC structure. Atomic weight is given 63.5. Atomic weight is given 63.5 grams per mole. Atomic weight is given 63.5 grams per mole. Then they are asking theoretical density of copper. Right. Avogadro's number also not given. See, I'll take Avogadro's number. Avogadro's number is equal to 6.023 into 10 power 23 atoms per mole. Okay. Okay, now this many number of atoms are there in 1 mole. Now, first of all, I'll calculate volume of unit cell. So, volume of unit cell is nothing but A cube. But A is equal to what? 2 root 2 R whole cube. Right? A is equal to 2 root 2 R whole cube. So, from this, by calculating this, 16 root 2 R cube. 16 root 2 R cube. R is given in the question. Now, in the options, it is given grams per centimeter cube. Na? So, this R value I can write in centimeter 0.128 into 10 power minus 7 centimeter. Minus 9 meter. Minus 7 centimeter. So, that I am substituting 16 root 2 into 0.128 into 10 power minus 7 whole cube. R cube it is, whole cube. Now, from this, listen, from this 16 root 2 into 0.128 whole cube into 10 power minus 21. 10 power minus 21. So, let us consider, I will calculate first volume of unit cell. I will calculate. Okay, let us consider. Volume of unit cell I will consider. So, 0.128 whole power 3 into 16 root 2. How much? 4.745 into 10 power minus 2. Okay, 10 power minus 2 is there. So, 4.745 into 10 power minus 2 already there. So, 10 power minus 3. Now, I am substituting in this data, in this question. See here, rho equal to number of atoms 4 into atomic weight 63.5 by Avogadro's number 6.023 into 10 power 23 into 4.745 into 10 power minus 23. So, plus 23 minus 23 is going to be cancelled, and from this From this 4 into 63.5 ANS divided by 4.745 into 6.023, 8.88 grams per centimeter cube. So, out of these 4 options, the C option you will get the correct answer. Okay, na? Out of these 4 options, C is the correct answer. I hope you understood. This question, this concept is very, very important for GATE exam. Definitely they will ask question. Okay, na? Everyone understood? Is there any comment? Please, if you have any doubt, please ask me here. Please let me know. If you have any doubt, please let me know. Right? Now, next question. Now, next question you can take. Now, in an iron cementite phase diagram, okay, at 728 degrees Celsius and 0.8% of carbon, one solid transforms into 2 other solids at eutectoid point. Okay, the degree of freedom at eutectoid point is. So, they are asking the degree of freedom at eutectoid point. Now, listen. Let us consider iron cementite phase diagram. Let us consider the iron cementite phase diagram. Here, listen, this is 0.8% of carbon and the temperature 728 degrees Celsius. Okay, na? At this point, at this composition and at this temperature, gamma iron is one solid, transforms into, the gamma iron transforms into alpha iron and cementite. Gamma iron transforms into alpha iron and cementite. So, at this point, it has 3 phases. Iron carbon alloy has 3 phases: gamma iron, alpha iron, cementite. So, what is the Gibbs phase rule? To find the degree of freedom, we are using a Gibbs phase rule. But here, general Gibbs phase rule, remember, general Gibbs phase rule formula is Gibbs phase rule. If I consider F plus P is equal to C plus 2, this is applicable for water system, carbon system, because water and carbon will generate different phases by changing both pressure and temperature. So, 2 is there. But an alloy will generate different phases by changing temperature and chemical composition at a constant pressure. That's why we should use modified Gibbs phase rule. In case of modified Gibbs phase rule, if I consider here F plus P is equal to C plus 1 for modified Gibbs phase rule. Why? 1 degree of freedom we are reducing. Now, I am using this concept. Tell me, number of phases at exactly at this point, 3 phases are there. What are those? Gamma iron, alpha iron, cementite. Number of components are 2, that is iron and carbon. If I substitute these values here, I will get degree of freedom is 0. 0 degree of freedom I will get. So, here out of these 4 options, the degree of freedom is 0. So, this is the correct option for this question. So, remember, at an equilibrium reaction point, you can take a peritectic point, eutectic point or eutectoid point. Degree of freedom is 0. Degree of freedom is 0. I hope everyone understood this question. Okay, na? Everyone understood this question, right? Now, listen. Next question. See here. Find the strain hardening exponent N in sigma equal to k epsilon power n for an alloy in which the true stress of 415 megapascal produces a true strain of 0.10, assuming a value of K 1035 megapascal. So, see, actually, listen, if I consider the engineering material, okay, up to the elastic limit, the engineering material follows the Hooke's law. It's a linear line. But after the elastic limit, material is a parabolic line it follows. In this region, material follows power law. So, here power law is what you know? Sigma T is equal to K into epsilon T power n. Here K and n values are constant. And sigma T and epsilon T values are going to change. So, in this question, they are asking strain hardening exponent. They are asking strain hardening exponent n value by using this equation. Equation also given in this question, very simple question. Okay, now see here, true stress is given in the question. How much is given true stress? 415 megapascal. So, true stress is given 415 megapascal and true strain is given, that is 0.10, right, and K value is also given, that is 1035 megapascal, right. It's a very simple question here, very simple question. Now see here, sigma T is equal to K into epsilon T power n, that is 415 is equal to 1035 into epsilon T is how much? 0.1, okay, whole power n. This value they are asking. Now see here, I'll simplify this. 415 by 1035 is equal to 0.1 whole power n. Apply natural log on both sides. So, ln 415 by 1035 is equal to n ln 0.1. So, n is equal to, from this, n equal to this by this. So, ln 415 by 1035 divided by ln 0.1. So, what is the answer here? What is the answer? It's a very simple question here. Only the thing you should know how to use this equation, how to solve this equation. See, ln 415 divided by 1035, okay, I got one value, then ns divided by ln 0.1. So, I got finally 0.396, 0.396. So, the n value for this question, 0.396. So, this is the question from the power law. So, for GATE exam, definitely they will ask you questions from the power law. That is very important concept. Power law of strain hardening concept is very important. Okay, na? Don't forget. Next, let us consider a question here. A cylindrical specimen of steel having an original diameter of 12.8 mm, original diameter 12.8 mm, is tensile tested to fracture and found to have an engineering fracture strength of 460 megapascal. Engineering, ultimate engineering strength, they are given 460. If its cross-sectional diameter at the fracture is, if a cross-sectional diameter at the fracture is 10.7 mm, determine the ductility in terms of percentage reduction in area. In the question itself, first of all, how will you measure the ductility? Ductility is measured in two ways. One is percentage elongation, how much elongated in terms of length, means final length minus initial length by initial length. Second is percentage reduction in cross-sectional area, right? Percentage reduction in cross-sectional area. So, here already they are asking percentage reduction in cross-sectional area. So, ductility is measured by percentage reduction in cross-sectional area, means A naught minus A1 by A naught into 100. I can simplify this. 1 minus A1 by A naught into 100. Again I will simplify this. 1 minus A1 is what? Pi by 4 D1 square. A naught is what? Pi by 4 D naught square. So, D1 by D naught whole square into 100. Now, from this 1 minus D1 is how much, you know? D1 is 10.7. 10.7. D naught is 12.8 whole square into 100. Now, what is the answer? What is the answer you can take here? What is the answer you can take here? 10.7 divided by 12.8 whole square. 1 minus answer. So, you will get here by multiplying with 100, 30.12 percentage. Okay, 30.12 percentage. In case in the question if they asked like ductility in terms of percentage elongation, definitely they will give initial length and final length, so that you can write final length minus initial length by initial length into 100. We can also use this formula. I hope you understood. Understood now? Next question. Now, see here, for a lead tin alloy of composition 80 weight percentage of tin and 20 weight percent of lead. 80 weight percentage of tin and 20 weight percent of lead, and at 180 degree Celsius, determine the mass fraction of alpha and beta. So, they are asking calculate mass fraction of alpha and beta. So, very simple question it is. See, 80 percentage of tin, 20% of lead. So, this is 80 percentage of tin, 20 percentage of lead. Okay, 80 percentage of tin. Now, where they are asking, you know, at 180 degree Celsius, strictly speaking, this will takes place, this line, eutectic temperature line, if I consider 183 degree Celsius, or some textbooks 182 given, right. So, 183 is given here. So, 180 degree Celsius they are asking. So, if I consider 180 degree Celsius slightly below this line, so at this point we are going to calculate mass fraction of alpha and beta. So, this is alpha, this is beta. Okay, now we will calculate we will find the liver line first. So, at this point we are having alpha and beta. At this point we are having alpha and beta. Tell me, where will you get 100% of alpha as per this diagram? 100% of alpha I will get by drawing this line, it intersects this line here. Here 100% of alpha, C alpha. Where will you get 100% of beta? 100% of beta you will get here, C beta, right? C alpha and C beta, right? Now, let us consider the liver line. Let us take the liver line. Left side I will take alpha, right side I will take beta, okay? Now, C alpha this is C beta I will take, and this is C naught I will take. As per the question, C naught is given 80% of tin, 80% of tin. As per the diagram, C alpha is 18.3% of tin, 18.3% of tin, and C beta as per this diagram 97.8% of tin. 97.8% of tin. Right. Now, tell me, we should calculate mass fraction of alpha and beta. So, mass fraction of alpha I want to calculate. What is the hint, what is the trick to calculate alpha without remembering the formula? What I said, if I want to calculate alpha, alpha is on the left side, so take opposite half of the line. Alpha is on the left side, so take opposite half of the line. So what is that? What is that? C beta minus C naught by total length of the line. Total length of the line, that is C beta minus C alpha. Simple. If I want to calculate alpha, take opposite half of the line, then divided by total length of the line. Now, I'll consider here C beta is 97.8 minus 80 by 97.8 minus 18.3. So, what is the answer here? I'll calculate. See here. Try to solve it. You people also try to solve it. 97.8 minus 80 divided by 97.8 minus 18.3. So, you'll get 0.2238. If mass fraction of alpha is 0.2238, then mass fraction of beta is nothing but 1 minus mass fraction of alpha. Mass fraction of beta is nothing but 1 minus mass fraction of alpha, that is 1 minus 0.2238. Okay, so that you will get 70, 0.77 point something like that you will get. So remember, if they ask you mass fractions, then you should type there only 0.2238. If they asked you percentage, you should type here 22.38. Be careful. Fill in the blank questions they'll ask you now. So read the question carefully. If they ask you mass fractions, then type there only 0.2238. If they ask you percentage of alpha, percentage of beta, then type there 22.38 like that. Otherwise, you will do error, you will get error, you will get mistake, you will get negative. Now, this is related to iron cementite phase diagram. I will explain this question completely. Any type of question you can solve. Okay, na? Now, see here. Consider 6 kg of austenite. So, 6 kg of austenite containing 0.45 weight% of carbon. 6 kg of austenite, in that it has 0.45 weight% of carbon, cooled to less than 727 degrees Celsius. Cooled to less than 727 degrees Celsius. Let us consider the graph. Let us consider the graph. Okay. The graph here it is like this. So, remember, this is actually gamma iron. Okay, na? Gamma iron. This is 728 degrees Celsius eutectoid temperature. Okay, 727 is given in the question. Now, 0.45 weight% carbon. Remember, here we are having how much it is? 0.8% carbon. So, 0.45 means somewhere else. Suppose I will take 0.45% of carbon is cooled from austenite to, just below the eutectoid temperature. So, they are cooling up to here. So, this is my required point C naught. 6 kg of 0.45% carbon steel is cooled from austenite to just below this temperature. Then what they are asking, what is the froeutectoid phase? Tell me, in this region, what is the froeutectoid phase? Tell me, in this region, we are having 2 microconstituents One is eutectoid ferrite, plus perlite. So what is the proeutectoid phase? If they ask you, what is the answer? What is the answer? Ferrite. Ferrite is a proeutectoid phase. Proeutectoid phase is what? Ferrite. Suppose above this, above 0.8, we are having proeutectoid cementite. Proeutectoid cementite plus perlite. Proeutectoid cementite plus perlite. Suppose if I want to calculate proeutectoid phase, I'll apply this lever line. If I want to calculate proeutectoid phase, I'll apply this lever line. This is alpha, this is perlite. So by using, I can solve proeutectoid phase. Now, second, how many kilograms each of total ferrite and cementite form? How many kilograms? Here they are not asking the mass fractions. Here they are not asking the mass fraction, they are asking how many kilograms of total ferrite and cementite. See, if you want to calculate total ferrite and cementite, you should consider this complete length of the line up to 6.67% of carbon. So here, listen carefully, C alpha, this is C cementite. If you want to calculate total mass fractions of alpha and cementite, total length of the line. Now we can take the lever line is this one, this side is alpha I'll take, this side is cementite I'll take, okay. Now C naught is given 0.45% of carbon. Now C alpha generally in the question paper, don't worry, they will give you the diagram, otherwise they will give this value. I'll take 0.025% of carbon. C cementite is 6.67% of carbon. Now I want to get mass fraction of alpha. Same principle, use opposite half of the line in the numerator, in the denominator total length of the line, right. So C cementite minus C naught by C cementite minus C alpha. Now see here, 6.67 minus 0.45 by 6.67 minus 0.025. This is mass fraction of alpha. But they are not asking mass fractions. How many kilograms? Total is 6 kg. How many kilograms they are asking? So that first we should multiply, we should calculate this. Then after that, see 6.67 minus 0.45 ANS divided by 6.67 minus 0.025. So we will get alpha is 0.936. Then mass of alpha ferrite, if you want, total is 6 kg, 6 into 0.936. So 6 into 0.936 will get 5.616 kg. If alpha is 5.6 kg, then definitely mass of ferrite, Fe3C, cementite, mass of cementite is equal to 6 kg minus 5.616 kg. So 6 kg minus 5.616 kg will get 0.384 kg. This type of questions they will ask you. Again, another question they are asking. This is the first total ferrite and cementite. Let us say perlite and proeutectoid phase. Now see here, perlite and proeutectoid phase, if I want to calculate, this is the lever line, right. So I'll consider the space here only, I'll take, I'll explain here only. So this is alpha, this is perlite. Here C naught is equal to 0.45% of carbon. C alpha is equal to 0.025 percentage of carbon. C perlite is equal to 0.8 percentage of carbon. Right? Then mass fraction of pro-eutectoid alpha I want to get, that is equal to alpha is in the left side, C perlite minus C naught by C perlite minus C alpha, that is 0.8 minus 0.45 by 0.8 minus 0.025. So what is the answer? Alpha, mass fraction of pro-eutectoid alpha I am calculating, 0.8 minus 0.45 divided by 0.8 minus 0.025, 0.4516, right. So if I multiply with 6 kg, I will get mass of pro-eutectoid alpha is equal to 6 kg into 0.4516. So here 6 into 0.4516 will get 2.797096 kg, and mass of perlite is equal to 6 kg minus 2.709 kg. So that 6 minus this one, so 3.2904 kg. I hope you understood. From the iron cementite phase diagram, they may ask you micro constraints like pro-eutectoid alpha, perlite, or sometimes alpha cementite, this type of questions. So in this 1 hour, I discussed most of the numerical part, okay, and all the best for your GATE exam.